Hello, welcome you all for Unit 3. Here in this video, we'll be running on a topic on distillation. Now, there are three parts in this chapter. Distillation, I have divided into three parts: Part 1, Part 2, Part 3, and Part 1. In this video, we'll be looking into the different aspects of equilibrium. That is, principle of equilibrium, basic law or rules related to the equilibrium, then boiling point diagram and equilibrium diagrams. We'll be coming across one special type of solar system called as azeotrope, and mathematical relationship between these equilibrium compositions, and based on that a numerical. Now, the distillation by principle, it's a separation process. When you do the separation, there are certain components inside the feed, inside a mixture. You want to separate it out. The separation is completely based on the differences in the relative volatility of the components. Difference in relative volatility in the sense a component may be highly volatile, another component may be low volatile, relatively low volatile. The highly volatile component is separated by heating it, so it is going to be a simultaneous heat as well as mass, that is heat and mass transfer operation. So you'll be providing heat to the mixture, which creates volatile component into vapor phase, converts volatile component to vapor phase. In fact, along with the more volatile component, less volatile component also, some amount of it is evaporated. That vapor is condensed and collected as a product. In the beginning you have a feed. Once the process is over, the distillation process is over, the product that you get, the after condensation, is called as distillate, and the remaining quantity is known as the residue. Okay, now this may happen. The product may be nearly pure component depending upon the relative volatility. If there is a large gap between the relative volatilities of two components, so low volatile component may remain there, highly volatile component completely it may get separated out, possible. But usually most of the other cases, if you see it, there will be a partial separation. That means the highly volatile component, or the more volatile component, let me say, that will be coming into the distillate. Along with that, the other component, which is which you label it as less volatile component, that also comes. So there will be separation, but it's not 100% pure what you get here. The concentration of that compound which is more volatile will be more in this, and in the residue it will be less. Yes, you have enriched or purified or increased the concentration of the product by using heat as well as mass transfer process. Now let us look into certain properties of the mixture, which is highly required here before you get to the equilibrium cases. Mixture, when you say it is a combination of more than two components, it could be a vapor phase or it could be a liquid phase, any phase, there will be minimum two components involved. When you have a component in a pure phase, it will have certain property, physicochemical property will be there. When the two components are there in a mixture, they remain as a mixture. Maybe mixture could be a solution or a suspension, whatever it is. In general, it is a mixture. Solution is a homogeneous phase, in fact. Now let me assume it as a solution. So in the case of a solution, there are two components A and B. When they exist as a mixture, their individual properties are lost. What they exhibit is the property of the mixture. So it depends upon the component A and B how the mixture property is behaving. If the components A and B are chemically similar, if their properties are little similar with each other, A and B, in that case the property of the mixture could be almost similar. But if the components are totally dissimilar, chemically dissimilar and physicochemically dissimilar properties, in that case the mixture property may be totally different from their individual components. Now coming to this particular property, partial pressure. Partial pressure is nothing but the component say for example a component A is there which is having which is in the vapor phase, it will exert some pressure, and it is obviously it is in the vapor phase. So that particular, at that particular temperature, that pressure, you can call it as vapor pressure. Now partial pressure is nothing but a component A, it is present in a mixture and it is exhibiting some pressure over there. So the pressure exhibited by that component in that particular condition within the total volume is considered as the partial pressure. Now if at all it was present in the total case, now individually A and B will have their own partial pressures exhibited by individual components. By Dalton's law, you can say that for an ideal mixture, ideal system, the total pressure will be equal to summation of the partial pressures. Now yeah, Dalton's law says that. So you'll have partial pressures, summation of partial pressures will be equal to total pressure. Other way also, partial pressure will be equal to mole fraction. In the entire distillation we'll be dealing with the mole fraction rather than mass fraction. So whenever you come across X and Y, they are mole fractions. So mole fraction of component A multiplied by the total pressure will be equal to partial pressure. So Y and X. So this is a standard notation that we use in the distillation throughout. What is this? Y and X both are mole fraction, but Y is related to the vapor phase, X is related to liquid phase. Now Raolt's law. Raolt's law is one law applicable for a ideal mixture. This is applicable for ideal mixture. What it says is the partial pressure of a component A is equal to the product of vapor pressure of that pure component, the vapor pressure of pure component multiplied by the mole fraction of that particular component in the liquid phase. So I have taken X here. X is the mole fraction in the liquid phase for that particular component. So if you write it for component B, it will be PB is equal to PB naught into XB. So individual components will have their own partial pressures. Now Henry's law, this is an equivalent law. Raolt's law and Henry's law are far apart, but looks similar. The partial pressure is equal to a constant called as Henry's constant multiplied by the mole fraction. One thing you keep it in mind, when you can apply Raolt's law, at that time you cannot use Henry's law. But if you use Henry's law, you cannot use Raolt's law. They are complementary to each other. Alright, so continuing with that properties of mixture, here you have one case. That is, mixture means usually it's a homogeneous solution. If you have a homogeneous case, it is a solution. Otherwise heterogeneous means you can have a suspension. But in distillation always we have homogeneous solutions. So homogeneous cases we get. There are two types of phases or two types of solution you come across always, liquid and vapor. The vapor has emerged from the liquid phase itself. So you have component A and B in the liquid phase. Same A and B will be available in the vapor phase. So it is not that one particular component is present in liquid phase, other is not the same thing is not present in the vapor phase. Not like that. Given a component is present in liquid as well as vapor phase, but the concentration of that will be varying. Now coming to this ideal solution, it's a type of mixture, ideal and non-ideal solution. How do we define it? Very simple. You take a homogeneous solution, homogeneous mixture or ideal solution if that follows Raolt's law for all the values of X. All the values of X in the sense X varies from 0 to 1, mole fraction of given component in liquid phase. So for A, XA varies from 0 to 1. Now if the Raolt's law is applicable followed by that particular solution, the solution is termed as ideal solution. If it doesn't follow that rule, then you can label it as non-ideal solution. It's simple. Now let us take the case over here. So you have one ideal solution, the straight line what you see is the ideal solution. So you can see that from 0 to 1 XB product of multiplied by PB. So this particular line is the partial pressure. So partial pressure, it's a straight line. It's a straight line equation. Now if you take this particular case, this is the non-ideal case. This is a non-ideal case. If it was Henry's law, if it has stopped Henry's law, it would have been like this dotted line. Now in reality, the ideal solution follows this particular line, blue line, purple line. The green one is the non-ideal solution. For some values, that is low concentration of B, it follows Henry's law. For high concentration of B, this is high concentration of B, it follows Raolt's law. So this one here, it at low concentration, approximately as XB tending to 0, a non-ideal solution follows Henry's law. As XB tends to 1, a non-ideal solution tends to be ideal, or it follows Raolt's law. Now we come across something called as constant pressure boiling point diagram. What it means is you have to plot temperature as a function of mole fraction of that more volatile component A, let me say, more volatile component in its liquid phase and vapor phase. So in the x-axis you have x as well as y. Both are plotted on x-axis, x and y, because x varies from 0 to 1, y also varies from 0 to 1. So the variation is same. So the y-axis is temperature. It is the boiling point that you are drawing on the y-axis. So that is why the name boiling point diagram. And this entire diagram is fixed for a given pressure, that is total pressure. So that's why we mention it as constant pressure boiling point diagram. We also call it as TXY plot. The reason is T temperature, X mole fraction in liquid phase, Y mole fraction in the vapor phase. Now it represents equilibrium composition of X and Y at different points. So this particular diagram, what it is representing is an equilibrium diagram for different combinations of X and Y in the liquid and vapor phase. The boiling point varies. As I told you earlier, for a given individual component, its thermochemical property remains fixed, constant. If it is in a mixture, depending upon the concentration, its individual properties are changed. That's what it's represented here. Now, before going into that, a given vapor pressure, it varies as a function of temperature. It's a function of temperature. Usually, so one of the commonly used equation is Antoine's equation, where vapor pressure is given as a function of time. Actually, almost all the equations start with the thermodynamic principle, and it begins with the concept of Clausius-Clapeyron equation. So if you're interested, you can go through that Clausius-Clapeyron equation, where it explains how the vapor pressure is dependent on the temperature, but it's not dependent on the total pressure. It depends on only temperature. So given the vapor pressure as a function of time, you can plot it. How we do plot it? Let us look into the equilibrium relations little later. So the x-axis here in this case is x and y of more volatile component. Please note this important aspect, more volatile, not all the chemicals. You have to identify the more volatile component first, then find its concentration in the liquid phase and vapor phase of the same chemical and plot it in the x-axis. Temperature is y-axis. What's so important in this? So there is something called as bubble point curve. Bubble point curve, this is Tx curve, and there is something called a dew point curve, that is Ty curve. So temperature versus x, temperature versus y. So that particular data, this particular graph represents temperature versus y. We call it as dew point curve. Temperature versus x, that is bubble point curve. This particular curve is called as bubble point curve. Any region below this curve, below this Tx graph, is called as subcooled region. In this region, in this particular condition, you take any mixture, it will be in the liquid phase. Above this is a superheated region. So above the Ty curve, you take any point, that will be in the vapor phase. But in between these two curves, you take any point, it will be in the equilibrium region. Equilibrium region means vapor and liquid coexist. Now say for example, I have a liquid of 0.2, that is 20% of more volatile component, another is 80%. Component B is 80%, component A is 20%, and that is existing at 80 degree. That means that we have only liquid phase existing there. There is no vapor available. On the other hand, I have the same composition at 115 degrees, say 115 degrees somewhere here. So that exists in the vapor phase only, no liquid phase there. Other hand, here somewhere in this case, that is 105 degree, maybe here. So there exists some amount of liquid as well as vapor. Both exist, they are in equilibrium with each other. So this is the concept of boiling point diagram. So these are the three regions: subcooled region, superheated region, and vapor liquid equilibrium. Let's look more into this particular aspect. That is BP, that is boiling point of the pure component, pure B and pure A. They are depicted here. So LVC stands for less volatile component. MVC stands for more volatile component. So for the more volatile component, the boiling point is this much. This is the temperature at which the pure component, pure A, boils. Pure B, it boils, that is the less volatile component. B is less volatile component. It boils at this particular temperature. You can see that boiling point is lesser for the more volatile component. For less volatile component, the boiling point is higher. So within these values, boiling point of pure components, within that zone or region, this entire VLE exists. Now let me take one simple case, A. Let me take the case of A. As I told you earlier, if you look at this, this is in the subcooled region. So this is the point where T is less than T1. T1 is, this is the point here. So it is less than T1. So here it is in the liquid phase. Now, if I heat this mixture, then the temperature is raised to T1. So it reaches point B. At T1, it starts evaporating. So it will be issuing little amount of vapor. It will issue little amount of vapor, and that will be in equilibrium with the C. So the concentration of that particular vapor will be this much. So that is 0.294 in the liquid phase, and the vapor will be 0.625. And further if I heat it, it will reach the point D, that is temperature T2. I will heat from T1 to T2, higher temperature. So D. Now within this region of VLE, it is unstable. That means it will separate into two layers. So it will form two layers, one layer of liquid phase, that is residue, another layer residue, that is liquid phase here. This is liquid layer TX, and this is TY. So it forms D to E, D to E this side, D to F. This F is vapor phase, this E is liquid phase. So the concentration in the liquid phase will be this value. What is this? 0.25, and vapor phase will have the concentration, this value, F for F, 0.538. So if I heat it to D, you will get liquid phase and vapor phase with this concentration. So what you observe is the concentration of Y decreases if I heat it further, the equilibrium. Further I can heat it up to this point, it will form completely vapor. Now this particular line, EDF or BC, this is called as tie line. Now you have something called as inverse lever rule applicable here too. What it gives is the ratio, it's a scale, that is you can use a normal scale and find out in centimeters. This distance DE and DF, this distance you can measure. The ratio between DE to DF will be equal to DE to DF will be equal to moles of distillate. So you have calculated DE here, this is distillate. So moles of distillate divided by moles of residue. So the molar ratio you can calculate given the inverse lever rule. Just pause the video and just ponder over this question. What could be the difference in amount of distillate produced at C and F? C and F. These are the 2 points. Pause the video and think. Okay, welcome back. I hope you have thought something about this inverse lever rule. If you look at the inverse lever rule here, the value next to this is left to this side is almost 0, whereas the D to E is some finite number higher than this value. Means the vapor quantity that is produced for this is very, very low. The vapor quantity produced for the case of F, it is high. So as you go up, vapors produced will be higher and the concentration will be lower. So this is going to happen if you increase the temperature. Then we come across vapor liquid equilibrium, VLE, or otherwise called as XY plot. So you have calculated X for more volatile component in the liquid phase, Y more volatile component in the vapor phase in the Y axis. And if you draw one X is equal to Y line called as a diagonal line, if you draw it, the vapor liquid equilibrium Y versus X, it will be on the upper edge like this. So this is for an ideal case. For an ideal case, it will be on the upper end. You need to remember or note that always two components x values xa plus xb will be equal to 1, and for a vapor phase ya plus yb equal to 1. For a non-ideal system, slightly there will be different, and usually they are called as azeotropes. What is this azeotrope? An azeotrope is a liquid mixture. When you vaporize it, it produces same composition as the liquid. So we have two types here, minimum boiling and maximum boiling, and I'll show you in the graph how it looks like. If at all it was an ideal solution, you would have got a TXY diagram up to here. This kind of connectivity will be up to here. But for a non-ideal solution, it intersects somewhere in between, not at the end, somewhere in between. Now at this point, if you take this particular case for a y-axis as well as x-axis, and if I say that the system exists at this point 78.2 degrees Celsius, 95.6%, if this exists at this point, concentration of that more volatile component in liquid phase as well as vapor phase will be same. In both the phases the concentration is same. That is what is azeotrope. It's a liquid mixture which when vaporized produces the same composition as the liquid here. Whereas if you take any other combination, for example here, if you vaporize, the liquid composition is this much, vapor composition is this much, C2 and C1, they are not equal. The C2 is greater than C1, whereas here if you try to make such a diagram, it is just a single line here, just like this, single composition, that will be 95.6%. So there are two types, as I said, minimum boiling and maximum boiling. This is an example. Ethanol water system forms minimum boiling azeotrope. So how do you know that it's minimum boiling azeotrope? Just draw the curve and you see that the boiling point is lesser than individual boiling point. Methanol boiling point is 78.5 degree. For water it is 100 degree. Whereas this azeotropic point is at 78.2 degrees Celsius, lower than both. So this is called as minimum boiling azeotrope. Now at 95.6%, which is a mass percent, or otherwise 89.4 mole percent, it is the same. This forms azeotrope. This is what we call it as rectified spirit. Rectified spirit, that's what you heard about. Now just think about how it could be maximum boiling azeotrope. Just think about that. You can pause the video and you can think of how does the maximum boiling azeotrope look like. Now this is a graph for x versus y. X versus y, for some point it goes up, it goes down. So it's not completely up above the diagonal line always. First it is above the diagonal line, then it goes below the diagonal line. Now this also for maximum boiling azeotrope, how does it look like? Just imagine it. Okay, let's have a look at it. Now this is the maximum boiling azeotrope. Now see this, the boiling point of the mixture is above the two individual boiling points, so that is why it is named as maximum boiling. The case example we are taking here is HNO3 versus water. So the nitric acid boiling point is 86 degrees Celsius, water boiling point is 100 degrees Celsius. Now in the XY equilibrium diagram, first the equilibrium line goes below the diagonal line, then goes above the diagonal line. So y is lesser than x here, y is more than x in this case. Now let us look the mathematical relationship between the compositions in two phases. Before we enter into that, let us make certain terminologies familiar. Remember, component A is usually more volatile than B. So whenever we take A and B as the notations, A is more volatile, B is less volatile. X is for the liquid phase, Y is for the vapor phase. That is mole fraction. Total pressure, let me denote it as capital P. Vapor pressures are denoted as P naught A, P naught B. So if you look at this P naught, it is vapor pressure for A and B, and they are functions of temperature only. Then if I use a Raolt's law, as I have already discussed with you, PA and PB, this is partial pressures of A and B. P naught A into XA, P naught B into XB. Now if I use Dalton's law also, that is mole fraction of vapor phase multiplied with the total pressure, it will be equal to partial pressure of A. So the other way of writing is PA plus PB is equal to P. Here it is, PA plus PB is equal to P for a binary mixture. Let us take binary mixture as the case throughout the distillation. That's the easiest way out to learn it. Binary mixture means a mixture, a solution having two components, A and B. So PA plus PB is total is P. Now let's combine the two equations. these two equations let us combine, and these two equations let us combine. That is PA is equal to PA this side. So this will end up like this. What do you get? YA is equal to P naught A into X, XA divided by P. Similarly YB. Now we know something about binary solution, that is mole fractions in a vapor phase or liquid phase. You take any phase, the mole fractions of the two you add it 1, mole fractions in the liquid phase you add it should be 1. Now let us take this particular case YA and YB, which we already written it here. Substitute into this YB, substitute over here YB. So P is common in the denominator, this P common I can take it to the other side of the equal sign 1. Second thing, this XB what I have written here can be written as 1 minus XA. XB can be written as 1 minus XA because of this. Now if I take this P on the other side, what I'll get, this P here, P will be equal to P naught AXA plus PB naught 1 minus XA. Now let me rewrite this equation in the form of XA because I need XA for my calculation. So just rearranging, I get P minus P naught B divided by P naught A minus P naught B. Differences in the vapor pressures, numerator, total pressure minus vapor pressure of the other component. So summarizing it, so for X and Y, for A, if I write X and Y as A, instead of XA and YA, I'll write just X and Y. I mean it's for A. So for B, I'll write it as, instead of XB, I'll write 1 minus X. For YB, I will write 1 minus Y. So that is easiest way out to write. So with respect to that, so this Y what you have written, I can write it as P naught A into X by P. Similarly, this X what you have written here, it can be written this way. And the total pressure can be written X and 1 minus X. So instead of 1 minus XA, I have written simply 1 minus X. Instead of XA, I have written only simply X. So these three equations will be used for our analysis. Okay, you can pause the video here and think about this particular question. You can pause and come back. Alright. Now the question is, can you plot TXY diagram using these equations? This is the TXY diagram which you are supposed to plot. Yes, we can plot it. You can see that vapor pressure is a function of temperature. Given the temperature, you can find out the vapor pressure. Given the vapor pressure, you can find out X and Y values using these equations, and you can plot it. How to do it? We'll solve a numerical and see. But before that, let us see one more topic called as relative volatility. What is this relative volatility? Volatility is nothing but the ratio of partial pressure to mole fraction in the liquid for A, or even for B, equivalent for B. Now that is volatility of A is equal to PA divided by XA, volatility of B is PB divided by XB. So partial pressure divided by mole fraction. In the liquid phase, we'll be writing it for A or B. Relative volatility alpha is nothing but ratio of these two volatilities, that is volatility of A divided by volatility of B. So rewriting this term, you can write like this. Now if you remember from Raolt's law, that is PA is equal to P naught A into XA, you can write alpha is equal to vapor pressure of A divided by vapor pressure of B. Now this partial pressure, you can write it as PA is equal to YA into P, that is our Dalton's law. PB is YB into P. Alpha, this alpha, now you can rewrite, that is this equation, I am using this equation I am using it now. So you can rewrite this, PA is equal to YA into P, PB is equal to YB into P. I am just substituting over here. P is common term, cancel it, YA XB divided by YB XA. So let us slightly rewrite this entire equation so that your Y comes on one side, X comes on the other side. So Y function of X with alpha in between. Still you can improvise this equation, because already I have told you YA, instead of writing XA and YA, we can write simply X and Y. XB and YB we can write it as 1 minus X. So that way also you can write it. So using that YA 1 minus YA, so you end up with this particular equation, that is Y is equal to alpha X divided by 1 plus alpha minus 1X. This is the equilibrium equation. It is something similar to what you get in Freundlich equation or distribution equation by extraction. Is an equivalent, that is a relationship between X and Y, the equilibrium equation. So it is alpha X divided by 1 plus alpha minus 1 x. So the previous topic we have seen 3 equations there, and this equation will be useful for solving a problem. So you can pause the video here and you can go through the problem, just read out the problem. I'll be back. Okay, welcome back. Hope you have read the problem completely. Try to understand how you solve it. So you are given with the vapor pressure data here, temperature versus P naught A and P naught B. The data is given. Total pressure is also given, 53.32 kilopascal. You are expected to plot TXY diagram, boiling point diagram, equilibrium diagram, XY diagram, and write an equation for y as a function of x and alpha. Alright, so we come across one important problem here, how to identify more volatile component. Because if you look at the data here, it is the data are given, there is no mention of whether A or B. Let me go back to the problem. There is no mention of whether A or B, which is more volatile. That is not mentioned. So let us try to identify which is more volatile. Based on the boiling point, you can check it out. Boiling point for more volatile component is less than less volatile component. So here there is no question of boiling points coming into picture directly in front of us. Now we can compare the vapor pressure. Vapor pressure for the more volatile component will be more than vapor pressure of less volatile component. In simple words, at a given temperature of A and B, whichever has the more volatile whichever has the more vapor pressure, that will be more volatile. The component having more vapor pressure is more volatile. So you can think which is more volatile here. Yes, you are right. A is more volatile because 53.32 greater than 21.25. So at a given temperature, you identify throughout it is true that A has more vapor pressure compared to B. So this is one of the easiest method to identify more volatile components. So you are expected to plot now TXY diagram, XY diagram. As I told you earlier, given the vapor pressure data, I have asked you to think about it earlier, how we do it, how you can do it. So TXY, XY and constant we can find out. So throughout X and Y are having this particular notation. We will be using X and Y. They are the mole fractions of A, X in liquid phase, Y in vapor phase. So solving it, total pressure of the system is 53.32. It's a constant pressure. Alpha is the relative volatility, P naught I, that is vapor pressure for any component I. So we have already written these equations. These equations we can use it in solving the problem. So how do you do it? This is the sequence in which you have to do it. So you can write the equation up. You don't have to memorize the equations. You can simply write this equation. How do we write this equation? P is equal to two partial pressures, PA and PB, partial pressures. By Raolt's law, partial pressure is equal to P naught of A into XA, P naught of B into 1 minus X. So that's how I got it. Just rearrange the equation in order to get X. You get this equation. This equation is a reordered form of this equation. So here, given the P total pressure, given the total pressure PA naught and PB naught, you can find out X. Once you know X, given the total pressure and PA naught, you can find out Y. Given PA naught and PB naught, you can find out alpha. At the end, you have to average that alpha value. So for this case, this value, the one single value at 311.5, it comes out like this. X is equal to 1, Y is equal to 1, alpha is equal to 2.509, just by substituting into these terms. Likewise, you have to do it for all other values. All the values of T individually, you have to calculate, do it manually and verify this data. So average alpha, this average of all these values is 2.421. So of the three questions we have that was asked, y is equal to f of x, I have written here y is equal to alpha x divided by 1 plus alpha minus 1x. It comes to 2.421x divided by 1 plus 1.421x. Now plotting the graph. So you have this value from the previous calculated value t, x, y, t versus x. So that is x in the x axis, or y is also in the x axis for txy diagram, temperature in the y axis, this temperature in the y axis. So you have to go up to 340 starting from 310. Don't go from 0, go from 310 to 340, so that this graph is expanded version. And always use 0 to 1 for x axis, that is x and y both. So it will be 0.1 scale. Always it is 0.1, 0.1 scale. Don't take any other scale in distillation. So this blue curve is Tx. Plot T versus X. First two rows, T versus X dots you get, connect it. First row and third row, T versus Y. You draw the points and connect them. So you get the Ty dew point curve. Name them. This is your Txy diagram. This X versus Y, these values, the green line what you see, the dots here, purple dots. So you draw them, and diagonal line, you draw it, first point and last point, that is 1 1 and 0 0. Draw it, that's diagonal line. Remember one thing, always take x-axis uniform, that is 1 centimeter is equal to 0.1 unit, 1 centimeter is equal to 0.1 unit for equilibrium diagram. Whenever you use equilibrium diagram, it is always a square plot. Remember this, it's always a square plot. 0 to 1, 0 to 1. In the case of distillation, it's always a square plot. Here you take 0 to 1 with the 1 unit is equal to 0.1, and temperature, the lowermost temperature, that is 300 or 310 up to 340 or 350, so that this is visible clearly. Yeah, that's the end of the this particular class. Here what we have learned about equilibrium, that is a distillation, how the process takes place, equilibrium, different definitions that are involved in the equilibrium curve, that is boiling point diagram, and xy, the relationship between the equations, that is vapor pressures, x, vapor pressure, and y, and relationship between x and y. Then we have seen solved a numerical to plot a bubble point, or sorry, it's a txy diagram and xy diagram. Yes. Thank you.